starting to discuss about the different pressure-driven membrane operation that we introduced last time. In most part of the system we are discussing, we always have a linear relationship between the transmembrane flux and the driving force. This is typical kind of relationship in which this J can be the flux or the flow rate, depending which kind of units you are using. P is a term of proportionality, is a phenomenological coefficient normally, expressing the permeability of the membrane. And D, on the zeta, is the driving force. It's the ratio between the difference in the force, can be pressure, can be concentration, can be an electrical field, divided by the thickness of your membranes. That means increasing the thickness, flux is decreasing. And this kind of linear relationship is valid for most part of the process we are going to discuss. Basically, you are already familiar with similar relationship. What is the Darcy law, which is a kind of phenomenological expression utilized in traditional filtration system. You have that the volumetric flux is proportional to a term that is this LP to the difference in the hydrostatic pressure applied across your membranes or your filter, having a thickness equal to zeta. Similar relationship exists with this fixed law, when instead of considering a difference in hydrostatic pressure, you are considering a difference in concentration. And so you have the same kind of relationship with D, in this case, as diffusion coefficient, which you are familiar, and you have a concentration divided by the thickness, again, of your membrane. Similar relationship exists if you are looking to the transfer of species with electrical charge, Ohm's law, in which K, in this case, is the electrical conductivity of your system. Phi, that is the difference in the electrostatic, in the voltage, and zeta is the thickness, again, of your membranes. So this kind of relationship are traditional, and they exist, and they control flux in most part of our membranes. What is interesting to consider sometimes, that on one side we say there is a simple linear relationship between fluxes and driving force. But this situation is not so easy. In some cases you can have an interdependence relationship between your fluxes and the driving force. And this is creating some opportunity to realize also some membrane operation, basically as reverse osmosis and osmotic process, for example. The example of this interdependence is that when you create a concentration gradient across your membranes, you can have on one side, you're just producing a flux of your matter, of chemical substance, across your membranes, but also you can just realize, if you build up a system in which this flux across the membranes is going in a closed chamber, for example, this flux can just produce the growing of an hydrostatic pressure, and that's what we call osmotic phenomena. The same story, if you now, when you apply an hydrostatic pressure on one side of your system, on one side you can have a volumetric flux across your membranes, but on the other side, you can also create a concentration gradient. And that's what we call reverse osmosis. So in these two simple cases, you see that there is interrelation, interdependence between the fluxes you have across your membranes and some driving force that you have been applying. And we are just utilize this interdependence, for example, realizing reverse osmosis process. And today, more and more, you have the same kind of phenomena when you are talking about pressure retarded osmosis, producing energy. In producing energy, using osmotic phenomena, you can have the same PRO, pressure retardant, which is a way to produce electrical energy. That means to transform chemical energy in mechanical energy first and electricity second. So this interdependence is a quite important phenomena that we can just utilize in different situations. We have to give some definition about the property of our membranes to not only having some mass transfer across, but inducing some selectivity. That means some separation properties. Our membranes are selective, not only permeable, but they are permeable to some species and not to some other one. And this difference can be very high in some cases, so you can have separation of 99%, 100% in some case, or less effective, you can have separation of 40%, 50% of the different components. How we can define which kind of parameter we are using for telling this? We can define what is called a perm selectivity. And perm selectivity, as you can see here, this SAB, the perm selectivity between A and B, is given by the permeability of the species A and species B as a ratio of these two permeability. So you just define perm selectivity as the ratio between the permeability of A compared to the permeability of B. For non-porous membranes, for dense membranes, we define also permeability, which is nothing more than the product of, we mentioned already yesterday, last time, solubility and diffusivity. Assuming that in our membranes there is no size effect, only solubility and diffusivity are the two phenomena controlling our membrane transport properties. And in this case, remember that solubility is a thermodynamic parameter given by Henry Law, for example, that you are familiar, which is function of temperature. So we have to define the permeability at very changing temperature. You are changing the solubility. And that is just nothing more than the amount of penetrant that is dissolved, that is in the polymeric phase in the membrane, as in solution. When you dissolve salts in water, you can dissolve sodium chloride in a polymer, exactly in the same way. That is solubility. And that is just the term that, remember, is a thermodynamic parameter. The other one that is giving our permeability is diffusivity. Once that you have a concentration of your solute on one phase of your membranes, you apply what we say before, the Fick's law. So you are creating a gradient in concentration across your membranes, so you have a diffusion across this term and characterized by this diffusivity. So this diffusivity coefficient multiplied for the solubility is giving our permeability. And we will use more and more in reverse osmosis, in gas separation, in pervaporation, this term here, given always in the first approximation just by this product. Diffusivity is a kinetic parameter, solubility is thermodynamic one. Both of them are function of temperature. So you have, remember, to define permeability at a certain temperature. If you change temperature, the number will change. Separation factor, which is different from perm selectivity, separation factor is between the species A and B, is alpha A and B, is given by the amount of the species A in the permeate multiplied for the amount of the species B in the retentate, what is not going through the membranes, divided for the concentration of A in the retentate, that means in the concentrate solution, multiplied for the concentration of the amount of B in the permeate. So you can see here is not just the ratio of the two permeability, but there is a ratio between the concentration of species A in the permeate, downstream your membranes, divided for the same concentration of the same species upstream your membranes, multiplied for the reverse of the species B. This is a definition, and we have to consider this definition. The term that you will find more usually is what we call rejection coefficient. Rejection coefficient is the one when you have a table, or when you buy membrane, you will find this rejection given as a number. 90% rejection, 85% rejection. If it's nanofiltration, you will find 50% rejection for some species, etc. This number is nothing more, this is indicated as R normally, of the species A, 1 minus the ratio between the concentration of the species A in the permeate, downstream your membranes, divided the concentration of the species A in the feed, in the retentate, upstream your membranes, which means in the same form you can also write Ca in the feed minus Ca in the permeate divided Ca in the feed. So it's different in concentration of the species A during the process, initial one feed minus the one in the permeate, normalized to the concentration of the species A in the initial one, the one that when you're starting, okay? So all these terms, as you can see, rejection coefficient, separation factor, and perm selectivity, they are giving you the same idea what is going on across your membranes, but the numbers are different. So you cannot, when you're speaking about membranes and give some selectivity, you have to know if you're using rejection coefficient, is this definition. If you're talking about separation factor, is another one. So you cannot move the numbers from one definition to the other because the number will be different. The most traditional one, the one that is better you remember, is rejection coefficient because that's you will find very often. But you are familiar with the basic thermodynamic parameter we are going to use, but just to remember that when we are working in a membrane system, when we have a separation process, basically we are always working in systems which are not in equilibrium. You have just a system which is far from equilibrium by definition if I'm making any separation between different components in your system. Basically, we can understand what is going on in our system for approaching eventually the equilibrium situation using the basic thermodynamic equations. First law of thermodynamics, second law of thermodynamics, and the different term that you know already, but just to remember, and the first law of thermodynamics is giving the internal energy U as a function of the heat of the system and the work done by the system, and generally in this case you're using minus for the work done by the system to the external system, or done to the system. In this case, this term of the labor is indicated with a plus. So these are definition. You can also define just the opposite, but in our case, we will use this kind of definition. Minus is the work done by the system, and plus is the work done to the system. Another term that we are normally using is the Gibbs free energy, which is nothing more than internal energy plus this PV for TS, and S is a new term for you in this case, and S is just the entropy. And that is the second law of thermodynamics. And in second law of thermodynamics, you can define this ds as dq reversible divided by the temperature. For any reversible process, this is the definition of the second law of thermodynamics. The condition of equilibrium that we are trying to reach in any system is this one. When we are in equilibrium, which is not the case of our traditional membrane operation, the dg at pressure and temperature constant has to be equal to 0. So that's the definition of equilibrium in the basis of the two thermodynamics law. Remember that these two laws, what are telling us is that in any dynamic equilibrium, the one we are talking about are what they call dynamic equilibrium, different from the mechanical equilibrium, which is not dynamic. Normally we have two effects. One effect is the tendency of our system to reach a condition of a very low energy, potential energy. So the system is trying to, a stable system is the one with the minimum of the energy. The other one is to reach a situation of the highest entropy. That means the highest level of freedom for the system to move. And these two The highest level is given by the increasing of entropy. Entropy is giving the degree of freedom of our system, the degree of chaos. And the natural systems are evolving spontaneously to a condition of highest level of entropy. On the other side, they are also going to a lowest level of internal energy. The counterbalance of these two is given by an equilibrium condition that we can reach when the two tendencies are equal, basically, and that is what we obtain. The expression that we will utilize when we will define chemical potential or electrochemical potential are related to the definition of the Gibbs energy in differential term, and the term that is the one of our interest is what we call a chemical potential. The chemical potential of the system is the delta G related to the one component, to the delta Ni, at pressure, temperature, and composition of the other components constant. So this is the chemical potential of the species I. In a system with more components, the definition of chemical potential is nothing more than the differential of G on referred to Ni, constant, all the other components, J, and temperature and pressure. That is what is called the chemical potential. We can also define some they are called partial molar properties of the system, with nothing more than the entropy, or pressure, or volume, partial molar. And that is the kind of typical definition, and you will find this symbol, this line characterizing the term. It means that it's a partial molar, referred to 1 mole of each component, and Avogadro numbers of elements of the system. The total differential of the Gibbs free energy is this kind of expression, where you have the delta G, which is a function of the delta G for the temperature and composition. They'll multiply delta G for refer to the temperature, to the composition of the other term, etc. So that's what we call a total differential of the G free energy. So we define it in a simple term, as normally done, the chemical potential in terms of the Gibbs free energy, as we saw before, in this way. We have one term, that is the chemical potential of standard, defined in specific condition of temperature and pressure, plus the dependence of the chemical potential of the Gibbs free energy from the composition. So there's one way to express this chemical potential at pressure, at temperature constant, but function of the composition. In the expression before, we are telling we can also assume that the composition for the other term is constant. That is the more general expression, that the one we want to use, where we can just assume that this term here is the chemical potential in a standard condition of pressure and temperature. That can be 1 atmosphere and 0 degrees centigrade, for example, plus RT log the composition of the system for the component I. Concentration is present here. Normally, instead of using the concentration or molar fraction, as normally is X, you have to use, if you want to be correct, the activity. And the activity, you know, is just the concentration multiplied for the activity coefficient. The activity coefficient is giving you the fact that the concentration and activity are not equal normally. If you are not working very dilute solution, there are deviation with concentration from the ideal value, and that is what is measured through the activity coefficients. So if you want to talk about the concentration can be utilized in this expression, the chemical potential, only if you are in ideal solution. If you are not in ideal solution, which is the case, for example, when we are working on high concentration. When we will discuss about membrane distillation, I will show you immediately the expression that correlate activity coefficient with concentration, because in membrane distillation you are working at a very high concentration, and if you want to measure the driving force, if you are using concentration, you make significant mistakes. So you have to learn how to re-elaborate your equation in terms of the real activity, which is the one that is present in the chemical potential of our system. In general, if you're working on a solution 10 to the minus 1, 10 to the minus 2, etc., concentration and activity are equal. That means activity coefficient is equal to 1. In all the other situations, this term gamma will be 0.8, 0.5, 0.2, etc., and you have to measure or to find in the handbook which is the real value, which is easy for relatively low concentration, not easy at all high concentration. Sometimes you don't find any interesting relationship, you have to measure by yourself. And you will learn how to measure in some case. Now, the flux of our ions in the system is just nothing more, is given by the J, is given by the change with time of the composition, the species I, upstream, on one side of your membranes or on the other side of your membranes, divided for the membrane surface. And that's what we normally are considering the flux. So the J is nothing more than this divided for the membrane surface in the system, assuming that we want to measure the transfer of a component I from one side of our membranes to the other side of our membranes. Let's see some typical situation that we will discuss during our example of membrane separation. One of the most important equilibrium or non-equilibrium system that we are going to study will be the osmotic one. We can have, talking about osmosis, of osmotic equilibrium, osmotic pressure, and reverse osmosis phenomena. So all these are different aspects of the same kind of phenomena. Which is the phenomena? If you have a membrane which, following the definition before, is selective for the components dissolved in the solution, for example, a semi-permeable membrane is a membrane that in terms of rejection has a 99.9% selectivity for sodium chloride. That means water is going across. Sodium chloride cannot pass the membranes. In this case, if you have these membranes divided, a solution at a certain concentration with, on the one side, C1 is higher than C2, what is happening in the system for reaching the equilibrium in which the two chemical potential has to be equal, the only way for the solution to approach a situation in which the chemical potential is equal is to move water from the diluted solution to the most concentrate. Because in this case, we dilute the concentrate solution approaching the same chemical potential of the water. There's no other way of doing because salts cannot go across the membranes. If the membranes is not present, this situation would be easy approaching equilibrium just by mixing. If there is no membranes, or if membranes with big hole, there will be convection and the system will reach equilibrium chemical potential quickly. If there is a membrane, it does not happen if it's membrane high selectivity. The only way is that some water will move from the more diluted to the more concentrate, trying to arrive to this kind of equal chemical potential on both sides. And we're doing this, assuming that there is no difference in hydrostatic pressure between the two solutions. What is happening that we have a difference in the osmotic pressure between the two solutions. And that's what we call osmotic equilibrium. And the flux will be from the diluted to the concentrated, basically. Fresh water is entering in the seawater. That's what nature is doing from a long time to create energy, basically. The other equilibrium, the situation in which we have no flux across, is the one in which if we have a difference in hydrostatic pressure equal to the difference in osmotic pressure across the system, in this case, we will have basically a difference in concentration across, creating a difference in osmotic pressure, and we have to apply a difference in hydrostatic pressure equal to the difference in osmotic pressure. In this case, we have an osmotic equilibrium, and the flux across the membranes will be zero. The case that we like today is the case of reverse osmosis. In reverse osmosis, what we want to do is to extract fresh water from the sea, just the opposite of what is happening in normal osmosis. For doing this, what we have to do is to apply an hydrostatic pressure on the seawater higher than the difference in the osmotic pressure, in such a way that the tendency of the water, fresh water entering the sea will be just destroyed by the tendency of the water to go out from the sea, having a hydrostatic pressure higher than the difference in osmotic pressure. That's why we call reverse osmosis. Again, that's the same situation I described before. The only way, we have high pressure on the sea, so we have a convection to the membrane surface and we try to go across. But salts cannot go across. Membranes still have a rejection 99.9, so no salts can enter the membranes. Only things that we can do, applying the hydrostatic pressure, is to move water across. So water will go across, but the real pressure we have to apply for having water going through has to be higher than the osmotic pressure, because if it's lower, water will enter. More or less, depending from the level of hydrostatic pressure we apply. Remember, we have a pressure-retarded osmosis, and we will discuss about blue energy, which is just a phenomenon between reverse osmosis and normal osmosis. Pressure-retarded is a way to obtain some pressurization in a situation intermediate between normal osmosis and reverse osmosis. This phenomenon here, normal osmosis, is what today you find sometimes in the literature called forward osmosis. Remember that forward osmosis is osmosis. This term forward is to try to be more original, but it's nothing different than just osmosis. Okay? So these are the kind of phenomena that relates to the osmotic process, and particularly we will discuss the equation, the mechanism that control the reverse osmosis, and when we will discuss about blue energy or forward osmosis, also about just osmosis. This is the case. Normally, if you want to make the experiments at home, it's easy to realize. Now, the equation that we have, that is the osmotic pressure of the solution, is proportional to the activity of the solvent. This is what is called Van 't Hoff equation. The Van 't Hoff equation is telling you that this osmotic pressure is given by a relationship very similar to the one characterizing gas transport phenomena, Van 't Hoff equation. And that is R, universal constant of gases, absolute temperature T, divided for the volumetric, for the partial volume, and for the log of the activity coefficient of your species. If you want to observe this, the situation that you have, here is a selective membranes, and in osmosis what you have is the water and solution on the other side. And the strange phenomenon you observe, if you are not familiar with what is happening, is that you will see that the level of, on the sea side, on the constant side, is growing. And approaching one point, a steady state, apparently, it's not really, but just a quasi-steady state, keeping this difference in the hydrostatic pressure, which in principle is against what you learn in hydraulics, the law of the communication. In principle, you are supposed to have this level at the same altitude. It's not if you have a membranes inside, because we understand there is an osmotic equilibrium. If you want to, in this case, we are losing fresh water entering in the seawater. the same that happened in forward osmosis. If you don't want this, but you want to produce water, you just have to apply here on the seawater a pressure higher than the difference in osmotic pressure. So water is going out, only water, no salt, because the membrane is selective. And so you will extract the water. This kind of the Van 't Hoff equation can be just is approximate in the for dilute solution, where this activity is becoming just the concentration. So this is the typical equation. And sometimes you have to introduce this term that is called Van 't Hoff coefficient, because assuming if the membrane is ideally perm selective, selectivity in 100%, you don't need G. But most parts of the membranes are not ideal. So if you're doing experiment, osmotic experiment, you have to introduce a deviation coefficient related to the non-ideality of the membranes you are utilizing, which can be, instead of 1, can be just 95, 96, etc. So this is a term giving you deviation from ideal related to the membrane performance, because here is just question of the membrane performance. If you plot the solvent flux across your membranes as function of the hydrostatic pressure that you apply in the system, you always have this kind of behavior. And this is important because this kind of behavior is telling you two things. That if you want to operate in reverse osmosis, that means if you want to extract water from the sea, you always have to operate with hydrostatic pressure higher than the osmotic pressure difference. Because if during your process, for any reason, and this reason is called concentration polarization phenomena, this problem exists, it's very real. And if you don't control what is called concentration polarization phenomena, your membrane, still ideal, still very good, does not extract water, but you are just working on the other side of your pot, in this negative side where water is entering the sea. So when you make your calculation, you have to calculate your hydrostatic pressure for a certain level of concentration of the solution. If for any reason the concentration of the feed is increasing with time, you must be careful that you have to increase the hydrostatic pressure. Otherwise, you are going to operate down here. And so the water will just go on the other side. Interfacial phenomena can take place in your membrane system because when you extract water, some of the salts that are not going through the membrane will accumulate on the membrane surface. And they were not easily redissolved in the solution. So you build up in all membrane separation what is called concentration profile in the solution, in the feed. And this concentration profile are at the origin of this kind of problems. Concentration polarization. So ideal membranes don't work if you don't use the appropriate driving force. The same problem can exist with temperature. Not in reverse osmosis, they are also present but negligible, but in membrane distillation, you don't have big problem with concentration, but you have big problem with temperature. Exactly the same kind of phenomena. If the temperature difference across the system is not enough, you can have flux in the other side, and thus you don't operate your separation. So these are nothing to do with the membrane performance, has to do with the system, with the flow dynamic of the system. The way to avoid this kind of problem is that you never work at dead flow. You're always working with a cross flow in your membranes to destroy as much as possible, to facilitate the redistribution of the ions which accumulate on the membrane surface in the volume of your solution, okay? And that is one of the most important parts of this story. We already discussed these things, and that's the way in which you normally operate all the pressure-driven membrane operation and also the other one. Normally, when you are talking about a separation process based on membranes, you have your feed solution, you have your membranes in a module. You will never see the membranes probably. That means you have a module in which there is the membranes. And what is happening here
that your feed solution, which is just an homogeneous system, will be divided in two streams. One you can call retentate, which is the system in which all the species not going across the membrane will accumulate. One that we call permeate or filtrate, in which are all the species that go through the membranes. And that is the situation that characterizes all the membrane operation. You can see here that is already clarified that we never work with the normal flux to the membrane surface. We always work in this way, which means with cross flow. The solution is running at high velocity. Sometimes you are running here 5 meters per second. The linear velocity can be very, very high, depending on, very often you work in a turbulence, not in laminar flow, to destroy the concentration phenomena at the interface, which can kill your separation. So, but that is the general scheme. Again, remember the rejection coefficient is the term we are using, and the rejection coefficient has to be equal or eventually a little bit lower than 1, and it's just given by the concentration of the species you want to separate in the feed minus the concentration in the permeate divided the concentration in the feed. So this is just a relative value, the difference between initial and final concentration in the feed normalized to the concentration in the permeate. Another parameter which is very important, and we heard already different times, is what we call recovery ratio. The recovery ratio, we know one of the motivation for having reverse osmosis competing with thermal system, for example, I mentioned many times that the recovery ratio in reverse osmosis is of the order of 50–60%, relatively very high compared to normal distillation. In normal distillation, MSF, MND, you have a 20, 10, 30 at most recovery ratio. Having 50, 60 or more if possible, and we mentioned already, we will discuss about membrane distillation, because membrane distillation, the recovery factor can be 95%. What does it mean? The recovery ratio is the ratio of the filtrate to the feed volume, which means that if you have 1 cubic meter of seawater, if the recovery ratio is 10, it means that only 100 liters of the 1,000 liters are becoming fresh water, and the rest 900 you have to put back in the sea, which is not nice. But there was nothing to do with the thermal system. With reverse osmosis, we will see you can operate with 50–60%, and now you understand why, because if we are increasing too much, the osmotic pressure is increasing too much, and the pressure you have to apply is becoming 300 atmospheres, etc. No way, everything is too expensive, it needs stainless steel tubes of 2 centimeters, etc., no way of doing. But up to a certain value can be done. And so we work now with about 50. That means if you have 100 cubic meter, 50 cubic meter will be fresh water, and 50 cubic meter will go back to the sea, which is interesting. However, we are working today for having recovery factor 90, 93, 95. That means if you have 100 cubic meters, that will be 95 cubic meter fresh water and only 5 cubic meter back to the sea. These 5 cubic meter are the concentrated one, what is called a brine. And these are a big problem today. One of the big problems in desalination, we mentioned already in the introduction, is brine disposal. What to do with all the concentrate? Because when they are relatively low amount, you can put back in the sea or underground, or you distribute on the ground, etc. But today, with huge plants producing millions of cubic meters, etc., cannot be done anymore, and we have to invent, to develop a new solution. And one of the new solutions we will discuss will be just to utilize the brine. The brine means a lot of salts, and these salts are necessary. So if we find a way to utilize the brine at low cost, and if there is a good quality, that can be interesting solution to the brine disposal problem, which is issue number 1 today all around the world in desalination. So now we know what is a recovery ratio. Obviously, in every membrane operation, if you want to be sure that everything is going okay,
mass balance has to be very well respected, and we'll see in some cases also electron neutrality if the membranes are charged. But in this case, no problem, only mass balance. Mass balance is telling you that your feed, which is given by the concentration of one component in the feed for the molar volume, has to be, across the system we saw before, is splitted in two different volume. One can be the retentate, that means the concentration in the retentate multiplied for the molar volume, and in the permeate. So the same, all the components that were present in the feed are distributed in the permeate and in the retentate. If this mass balance does not work, something's wrong. Somebody made a mistake somewhere. The calculations are wrong. You have leakage somewhere, etc. But that is a check that you have to be always valid. You can find in the literature, or you can invent a new way to plot your results depending what you need. You can see here that from the definition of rejection and from the definition of recovery factor, you can also try to plot your experimental results in terms of retentate concentration of your chemicals, or in terms of permeate concentration of your chemicals, and you will have this kind of graphical representation. This is the ratio of the retentate compared to the ratio of the ratio between concentration of the retentate on the feed at constant rejection, 99, 50, and that's increasing the recovery rate, increasing the amount of water that you extract from the system, you will have this kind of dependence, which is a function of the selectivity of your membranes and of the recovery ratio that you can realize. So if you want to have very high recovery ratio, you need very selective membranes, and you obtain high concentration in the retentate compared to the one in the concentrate. You can plot just the opposite, concentration in the permeate compared to the concentration in the feed as function of recovery rate at different rejection, and you see just the same presentation opposite to the one. Here, if you want to have a high recovery ratio and you are looking what happened to the permeate, obviously for high selectivity you have a very, very low value of the rejection in the system, and in this case that is just the opposite than the one you have here, because that means that here in this case is a permeate concentrate in the permeate, which has to be relatively very low if you have a rejection very high. Just the different, these are just, you can invent other way to present your results. One way to plot your experimental result that can be useful sometimes is the fact that it's difficult to operate with membrane with 100% selectivity or 90% selectivity. So always you lose some of the solutes in the permeate, and you want to know sometimes how much of your solute is lost. So what you can also plot here is that due to the fact that the membranes are not 100% semi-permeable, as we defined before, the quality of the permeate is not 100%. If you want to produce ultra pure water for the electronic industry, for example, that's a typical case. In ultra pure water for the electronic industry, the loss of solute has to be zero. No way. If there is any very, very small, it's no more ultra pure water, and the electronic industry cannot utilize anymore. I don't know that if you are familiar that one of the largest applications today in countries as Japan, most part of the water initially produced through reverse osmosis was for the electronic industry. The reason for which Japanese years ago, today is no more valid, were #1 in electronics, because they have been inventing first the utilization of reverse osmosis in the cleaning of all the equipment, all the parts of the electronic system. And the Texas Instrument was normally losing 30–40% of the small device, and they were not understanding why, and they were not working correctly due to a phenomenon called white spots. If we have time, we will describe. The Japanese were 3% lost for white spots, and they were invading the market. People learned, and they understood what was going on, and they learned that the story was the Japanese already in the middle of the 70s, the early 80s, they were producing a lot of reverse osmosis plants, not for drinking, for electronic industry, producing water of very high quality, avoiding white spots. A white spot means that also if you have very good water, and at one part of the production line, you have to clean different small pieces, etc., with normal water. Distillate, B-distillate, 3-distillate, not enough. When you make a coating, when you dry your piece, and you cover, at the very end of the story, all these electronics are covered with a coating with polymer. After some time, under this coating, there were appearing some small, you have to look on the microscope, white spots. What are the white spots? White spots were the fact that the coatings are always permeable a little bit to water. So with time, if any drops of water was still present on your electronic device, with time, on the coating, the water was evaporated across the coatings, and the salts, few molecules left behind, they were not going through the membrane to the coatings, were just forming, were precipitate at high concentration, creating the white spots. The white spots are just molecules present in the water at very, very low dilution that were concentrated when the water was evaporating across the coatings. And in a micro device, these molecules of salt were making shortage, just making electrical problems, and the parts were not working anymore. So this piece were 40% lost due to white spots, which was due to the quality of water not good enough for this kind of application. Today, this problem is solved, and you can compete again, but the Texas Instrument was losing with the competition at that time, was a typical case for this reason. Today, with the standard we have, also ultra-pure water is very different. You don't use anymore reverse osmosis, not sufficient. Because now with the new standards that you have for electronics, we have to remove also not only salts, not also sodium chloride or any other salt, but all the gas dissolved. We have to remove oxygen to a molecular level, no oxygen at all. For doing this, RO does not work. And so one of the first applications of membrane contactors, membrane distillation, was for the ultra-pure water for electronic industry, where you can remove oxygen through membrane contactors for the standard we need today. So this is a typical way of representation of the solute loss. That is the fractional solute loss delta expressed by the amount of solute loss with the filtrate divided by the total amount of solute in the feed solution. So this kind of delta, and this is the equation. That is the relationship through the, again, remember, rejection and recovery factor. So these two numbers that we defined before, rejection and recovery factor, are the one that just characterize the performance of your system in terms of solute losses, or as before, concentration of the permeate compared to the concentration retentate and vice versa. So these are the kind of presentation. Now, we described already 4 processes: microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. These systems are different one from the other. Basically, they are all pressure-driven membrane operation, but the transport properties across the membranes and some of the important the mechanism that is controlling the selectivity, very different. Microfiltration, we remember already, first of all, membranes are symmetric. And normally they are symmetric and porous. If we are talking about liquid, in a liquid solution where the solvent is water, these membranes have to be hydrophilic, microporous. But they can be just symmetric, no asymmetric behavior here. And the relationship here is just the volumetric flux. The volumetric flux across the membrane is proportional through this hydrodynamic permeability, this thermal proportionality, LV, to the driving force, which is delta P divided delta zeta, the same that we saw before. And we know that thickness is the thickness of the membrane, which means increasing the thickness, we are decreasing the transmembrane flux. So it's a reverse. Keep in mind that this is very general, except we will discuss some case in which this is not true. Today, if some of you has to design membrane distillation, for example, new membrane distillation, you will realize that this system is a little bit more complicated, and this relationship is no more valid. You have to increase the thickness of your membranes compared to microfiltration. Sometimes the membranes are the same, but when you operate porous microfiltration membranes in polypropylene and PVDF, in microfiltration, this has to be the lowest possible. In membrane distillation, you have to find the appropriate thickness, because in membrane distillation, you have another problem. You have heat transfer across your membranes. And so if you want to decrease the heat transfer, that means increasing the energy efficiency of your system, you have to increase the thickness. One way of doing is to increase the thickness of the membranes. You cannot increase too much, because you are also increasing the mass transfer resistance. But you have to find the optimum between the mass transfer resistance and the heat transfer resistance, because you want to reduce heat transfer resistance in such a way that all the energy that you are supplying to the system will be utilized to evaporate the water and moving across, and not warming the polymer. Warming the polymer is a loss of energy. Today, we are losing about 50% of the energy we supply in membrane distillation is lost for thermal conduction across the polymer, which we don't want. And one of the way of doing is to operate on this one. So remember, when we will discuss membrane distillation, or if you are making research on membrane distillation, you have to optimize the thickness to minimize the heat transfer across. Very different than microfiltration. This is basically the mechanism of transfer is nothing more than a viscous flow through the pore. So you can use the Hagen-Poiseuille equation, and this is the one that is just characterizing the system. What you have to remember that in this case, the parameter, the term of proportionality that we saw in our relationship, the LP, is related to the membrane porosity, to the size of the pore, to the viscosity of the solution, and to the tortuosity. Tortuosity is a term that normally is not so easy to elaborate, but all these terms are part of the LP. Tortuosity means that the pores are not all parallel and regular in most parts of the membranes, and this tortuosity is related to the morphology of the system, and that is the L divided the thickness of your membranes divided for the real thickness, which means in one case the total thickness is the small L, but the tortuosity is changing a little bit, and that can be longer than L during the pathway that is present. Another point you have to remember, if you make calculation with some accuracy, is that when you are talking about the membrane surface, the membrane surface useful for your microfiltration is not just the geometric membrane surface, because part of the membrane surface is blocked. You want to go through the pore, and that means you have to know the total area of the pore divided the total area, and this number is lower than 1, because part of the membrane surface is just non-permeable at all, because the permeation here is not solubility, diffusivity. When you are in reverse osmosis, these problems don't exist, because all the surface is available to the solubilization and diffusion. And when you're talking about microfiltration, part of the pore are open, and that's the one we are using. Part of the surface is not porous, and this is not useful for the microfiltration. So we have to define this membrane porosity, which is basically surface membrane porosity. Not only the overall porosity that you can measure, but just the surface membrane porosity. If you have only one pore and all the rest is blocked, membrane surface porosity is very low. So we have to realize membranes with a very narrow, very open membrane surface, which is the best, most interesting. But if you do this, you will learn you lose the mechanical properties. And our membranes has to work under pressure for 10, 15 years, not for a few hours in the lab. So you have to be able to find a system with a good mechanical properties and useful membrane surface. Ultrafiltration is a little bit different than microfiltration. First of all, in ultrafiltration, the membranes are starting to be asymmetric. And that's the reason for realizing high transmembrane flux, because we learned that transmembrane flux is reverse to the thickness of the membranes. And so if you can have a membranes where most part is very porous, you can see here, very open. So mass flux nodity resistance to the mass transfer is very low in this high porous system. And you have a very selective skin only on the surface, on the feed side of your membranes. In this case, the equation that we are applying is related to the thickness of the dense skin, not to the overall thickness. So this one can be 300 microns, 250 microns, but the real membrane is 3 microns, 10 microns. And so the flux can increase very much. The learning how to make asymmetric membrane has been at the origin of all the membrane engineering. Years ago, in the 70s, at the University of California, Sid Loeb and Surirajan, they invented asymmetric membranes. The asymmetric membrane was the origin of a system that was becoming of practical interest, because before the same material were giving transmembrane flux very, very low. They invented these membranes. Suddenly the flux was 100 times bigger of industrial interest. From this moment, everything started already in the 70s. But just to realize this asymmetric system. In this case, normally, when you have a symmetric system, some molecules don't go through, but they can also accumulate on the membrane surface, which was not the case in microfiltration. In microfiltration, everything is 0.2, 0.4 microns on the surface, big pore. So salts don't accumulate at all. So no osmotic phenomena. We have no situation which can increase in concentration of the salts rejected, and that means we have to take care of the concentration polarization. No problem in microfiltration. Sometimes problem can be here. So in principle, we have to assume that the osmotic pressure difference between the feed and the filtrate can be sometimes significant. So when you're making your experiment in real life with real solution, etc., if transmembrane flux are not the one you expected, and you can predict with some simple calculation, the origin can be osmotic pressure. However, in general, does not happen. But it can happen. You can have accumulation, and eventually we'll learn what is called fouling. Fouling means that you can deposit something. Let's assume in principle that there's no fouling, no osmotic phenomena. In the equation we have to write down, the volumetric flux, because our membrane is just given, remember the following equation, by the chemical potential gradient that we know how to write down, plus the hydrostatic pressure gradient. There are two kinds of phenomena which are present. We have an hydrostatic pressure gradient now because we apply a pressure, and we have the chemical potential gradient. And these are all the terms which are present. We can simplify this equation because normally the water flux across the membranes is equal to the volumetric flux. There is no significant solute flux, so we can assume that the water flux is equal to the volumetric flux. And so we can rearrange a little bit our expression. We can also introduce that the activity of the solvent in solution can be expressed in terms of the osmotic pressure that we know. And so we can just rewrite delta P minus delta pi, which is the effective pressure that is working on the system. Remember, delta P is the one moving in the other side, if there is an osmotic phenomena, by the way. Delta P is the hydrostatic pressure. So this is the chemical potential expression and the hydrostatic expression. However, normally, this term here, the volumetric, is the thermoproportionality. L water is much lower than the volumetric one. This is the maximum, so we can simplify, and basically you can cancel the osmotic phenomena. So this part here, which is with this volumetric, with this LW, is negligible compared to LV. So this term disappears, and so the overall volumetric flux can be expressed by this equation down here in ultrafiltration, assuming no osmotic phenomena. If there is any osmotic phenomena, this term here has to be introduced, and we have to take care of this one. That means some fouling can generate this kind of phenomena. Remember that some membranes, industrial membranes, in the 80s, 90s, were called dynamically formed membranes. They were membranes, ultrafiltration membranes, or sometimes microfiltration membranes, on which, on purpose, you can induce the formation during the operation. For example, in textile industry, during the operation, you can form a deposition of some chemicals which are inducing osmotic phenomena, dynamically formed ultrafiltration membranes. So these membranes have a rejection for the dyes of some in the textile industry. They were used with big tube. Union Carbide, which is a big chemical company, was using this kind of system. They commercialized in the textile field this kind of dynamically formed. That means this equation in which this term cannot be cancelled anymore. And they were using and applying in some operation. Normally, however, you can cancel, and so this is the equation that you have. A lot of membranes of this kind are available. That means before starting, if you want to make a research on new ultrafiltration membranes, check what already exists, because this is an area that is well covered, and there are membranes which can be inorganic, ceramic of any kind, can be polymeric, and you can see here they have a nicely asymmetric. The real membranes is the top skin here, which is, this is about 300 microns. This will be 10 microns, no more than this. Normally, in the real life, it's more than one layer. When you have to prepare membrane for mechanical, to obtain mechanical properties of interest and avoiding compaction phenomena, etc., you can have, you see here, there is one dense skin on the surface. There's an intermediate layer that can be the same polymer or sometimes different polymers. You can use some different polymer here, and finally, what is nothing more than a mechanical support. That can be a polyester, or can be some inorganic system sometimes. On this polyester, give mechanical strength to operate at 10 atmosphere delta P. This is doing the job. This membrane here, the thin skin of 10 microns, has no mechanical resistance. If you apply 10 atmosphere, everything is blowing up. So that is the structure, but you can have also in ceramic and in any material, but a lot. So before doing something new, check what it exists, and if you invent something, for example, high temperature resistance, or new way to control surface, roughness is very important. If you want to avoid concentration polarization, instead of working a very high linear velocity for inducing turbulence, you can induce local turbulence by increasing the roughness of the surface. Instead of having very smooth, you can have very rough. In some case, you can create some just small protuberance on the membrane surface at molecular level. That means few 10, 20, 50 angstrom of thickness, and this can operate as turbulence promoter, local turbulence promoter, and minimize concentration, polarization, fouling formation, etc. So there is all these parameters can be checked. If you invent a new way of doing, that's going to otherwise go in the market, and you will find a lot of membranes in polyether sulfone, in polysulfone, in PVDF, or etc., with a wide spectrum of operating condition and wide spectrum of porosity, 0.1 microns, and very often we will find 0.2 or etc., etc. So there is a lot of these things, and from different company, and satisfying the different requests for the specific application in terms of chemical resistance, hydrophobic, hydrophilic, depending from the situation. I told you that 100%, all of you, are living for this kind of membranes, because all of you is driving a car. All the car that you are driving are going through ultrafiltration. In one of the steps of the production, which is the electrocoating, where they paint your car. The painting your car is not done by painting. It's taking your car, making an electrode, becoming the metal negative or positive, putting in a bath, and by changing the bath different polarity, so the painting is moving on the membrane surface, on the car surface, and will make a nice homogeneous painting of your car. After this, you take the car, you move out, and you put another bath where you wash all the painting that was still there. This water years ago was going to the river, the cleaning water. Today is forbidden by law. You cannot make the river yellow, blue, or green. But the reason because all the cars are going through ultrafiltration today is because if you just reuse continuously the cleaning baths with ultrafiltration, you can recover the painting and putting again in the initial bath. Lifetime, instead of having 3 months, now is about 1 year. And you reuse continuously. And the quality of this painting, when it go back after cleaning and after ultrafiltration, is better than the initial one, because membrane is doing a job better than the producer. So you can reuse and reuse and reuse most part of your painting just in the bath. And in the meantime, what you discharge is clean water, it's not colored water. So and that is 100%. If you go in China, in India, in Europe, etc., an electrocoating ultrafiltration plant is always installed. And some of these membranes are doing the job. If for any mistakes you change the color, the quality of your color, instead of having a cationic painting, you have an anionic painting. And you forget to change the electrodes position in your ultrafiltration, and you put your car inside, in few seconds, you block everything. Because, in this case, the fouling phenomena, if you change the ionic character of your painting, you have to change the ionic character of your membranes. And if the membranes is positive, it works nicely with a negative, with the cationic painting. So it rejects the color. If you make the same, if you make the same charge, it will reject. If you make the same opposite charge, it will attract. So if you have positive and there is a negative, you will form a nice coating on the membrane surface. It happened. People change the quality of the painting. They did not inform the company, and they foul in few seconds everything. Big trouble, big tragedy, and after the solution was easy, change the polarity. That is a nice way to understand how the system works, by the way. But this is real life. It happened. Sometimes it's so stupid, but if there is no good communication, the people lost a lot of time. So just to show you, you will find in your notes a lot of membranes with all the different concentration, all the different separation factor, 500 Dalton, 1,000 Dalton, what they call cutoff. By the way, there's one term I did not mention before. You will find in ultrafiltration, molecular weight cutoff. This is the numbers. There is no rejection here. There is no permeability, etc. It's cutoff. Cutoff because we don't know how to introduce a more real way to measure the selectivity. Very difficult. And very difficult because the selectivity is very much related to the membrane properties, but to the property of the solution. Depending from the property of the solution, you can change the cutoff. So cutoff is a number, very phenomenological number, telling you that with these membranes, in this specific situation of temperature, of feed composition, etc., about 90% of the solutes is not going through. But this is very much related to the kind of material that you are using. If you change material, you can change cutoff. So it's very approximate but generic idea. Okay? To give you an example, a lot of biological substance, when in solution, they can have different space configuration. Protein, some polyelectrolyte, they just change. They can be linear, they can be globular. Now, changing the pH, what is globular can become linear and vice versa. That means when you're talking about cutoff in this case, I have no sense, because it's very much related to the configuration of the molecules in the solution. However, there was a big commission I've been working for years trying a better definition of the selectivity of ultrafiltration. No results until now because companies don't want to change and don't want to give too many information. So when you find cutoff, remember that if your membrane PVDF has a cutoff, this one, or 100,000, you have to read, measure how. Is measured with dextran at pH 5 or with polyethylene glycol at pH 2, etc. Because depending from the situation, if you're smart, you understand a little bit how is the real selectivity of your system. But this number don't give you nothing as a rejection. Rejection is much more clear, scientifically sound parameters. Cutoff is a very general, and you have to understand what does it mean. Anyway, all these membranes exist, and they have different kind of configuration. You can see that they can be modular, fibers, spiral wound, etc., and a lot. And they can operate with different. This is the module. When you're talking about this number, they are not the membranes. It's the module in which the membrane are assembled. And that means you have to know which is the membrane surface available in the module. And sometimes they don't tell you because they want to give the productivity, and so they don't tell how big is the surface because that will give some more information on the membrane properties. And they give you this flux, the cubic meter, that is flow rate, the cubic meter per hour that you can have across your module. Nanofiltration. So remember that in ultrafiltration, we decided that the osmotic phenomena in principle can be totally neglected because the pores are big enough and we can still have a viscous flow. Nanofiltration is again changing the spectrum, the situation. First of all, also nanofiltration, asymmetric membranes, but now the skin that we have, before we are still talking of a relatively porous skin, 0.1, 0.2 microns. Here now you have a skin which is dense, relatively dense, approaching reverse osmosis. Not just as reverse osmosis, but approaching reverse osmosis. So we have now a system that is asymmetric with dense skin layer. Remember that we will discuss now soon that there is one more thing in nanofiltration that we mentioned. Now we have to assume that most parts of the nanofiltration membrane are also charged. They are not neutral. This can be done with polyelectrolytes, which can be cationic or anionic. Or we can induce on the membrane surface here some charge, what we call charge density, a certain number of charge, positive or negative, for square centimeter or for grams of your polymer, depending how you want to measure. Charge density is becoming very important. If there is a charge, we are introducing one more control on the selectivity, which is called Donnan exclusion phenomena. Donnan exclusion. So some species, charge will go through, some other species will not go through. Some species with double charge will be rejected. The one with one charge will go through. We can separate with nanofiltration monovalent salts from bivalent salts. Very important in a lot of industrial application today, where there is a Donnan exclusion, so a kind of electrochemical process combined with typical phenomena. Here the same, exactly the same equation we saw before for the ultrafiltration. Chemical potential gradient and the hydrostatic pressure gradient is the terms that are related to our transmembrane flux. And the total volumetric flux will be given in terms of introducing the osmotic pressure in the activity coefficient here. So that is the equation that we have to consider. However, now there is something new here that we have to learn. If we are talking about the concentration at the membrane surface, this is something that we are not able to measure. Until now, in ultrafiltration and in microfiltration, these terms were not important because there was no interfacial phenomena. We cut down all the phenomena interface. In nanofiltration, this is not the case. First of all, we can assume, as before, that the JV is equal to the J water, so these two terms are equal. But now we cannot cancel anymore the osmotic pressure gradient. Now this term is present in our expression, and we cannot just assume that it can be neglected. So we have to express this term by this expression. That means diffusivity for the concentration RT, and so we have to rewrite the equation in this term. Now, in nanofiltration, where the pore size of the dense skin is of the order of lower, sometimes of 1 nanometer, very small, this term here is telling you that we can have significant rejection also for species as magnesium sulfate or any not only the monovalent, but particularly the bivalent will be rejected. All the amino acid, sugars, and a lot of other compounds that people are present in a lot of industrial production will not go through the membranes at all. So we have to consider the osmotic phenomena related to the presence of high concentration in the system. So this term cannot be neglected as we made in ultrafiltration, and so we have to take care of it. In this case, the simplification, what we can do is, so we have to rewrite the expression, but now we are considering this concentration of the species I in the membrane phase, because we have a difference between this concentration in the membranes and in the solution. So how to measure this one? We have no idea. You cannot measure easily. So we have to introduce in this equation a partition coefficient, this term here, where we measure the partition coefficients, which is a thermodynamic parameter, remember, the solubility of the penetrants, the species in the feed, in the membrane phase. For doing this, you have to know the concentration in the feed, the partition coefficient that you measure independently. In this case, if you know these two terms, you can also calculate the concentration of the species I in the membrane phase, which is a term that we have to know for calculating the transfer across. So this can be done. In doing this, however, I mentioned that at the concentration and the surface, we can have a charge. So we can have polymers as this one. These are what we call polyelectrolytes. And they are at the origin of our life, by the way, because we have in our body a lot of this kind of situation and a lot of this Donnan exclusion. It means that if you have a system as this one, where some of the charge in the system are fixed in the network of your polymer, some other one are mobile. Some of them have the same charge of the fixed one, and we call co-ion. Some other one have a charge different from the one of the fixed one, and we call counter-ion. Now, the number of counter-ion in this system has to be equal to the number of the fixed ions for respecting not only the mass balance, but electron neutrality. So for each negative fix, we need one positive mobile. In this system, however, if you analyze the system and you write the equation, you will arrive at a situation in which you can clearly show that the counter-ions cannot enter in this system. They will be rejected, because if they enter, there will be an excess. We are creating an increasing of the negative concentration, cannot be neutralized because the negative ions here are fixed. They cannot move out. If one positive ion is moving in, one positive ion will go out. And so electron neutrality will be always very well respected. But if a negative ion is trying to enter, the negative ion already present will not move out, and so you violate electron neutrality. This is called Donnan exclusion phenomena, and can be very well understood writing the same equation that we wrote before and applying in the electron neutrality condition. If you write this, you will arrive to the conclusion that depending from the ratio of the concentration of the charge fixed, what we call charge density, and the concentration of the external solution, you can have penetration or not having any penetration of the co-ion. So you create what we call membranes cationic or membrane anionic. This kind of effect is present in the nanofiltration and is at the origin of the, let me arrive to the end, we will make the equation tomorrow, of this conclusion here, that when you're discussing about nanofiltration membranes, the partition coefficient that we are measuring before is more complicated than the normal one. Partition coefficient, that means the concentration of your ions in the polymeric phase compared to the concentration in the external phase, is given by two terms. One is the normal one, size effect, as in ultrafiltration. The other one is a Donnan effect. It's related to the charge density and to the charge of the membranes and to the charge of the ions you are considering. So the system is becoming a little bit more complicated, and we have to analyze more carefully. Okay? Anyway, we will just discuss this Donnan equilibrium next time. We have to finish a little bit earlier today. Okay? one suggestion. I'm talking, sometimes I'm talking a little bit fast, and I'm talking in English. So for some of you, maybe, if you don't follow, don't hesitate. Don't just raise your hands, make noise, and you can try to clarify if something is not clear. But don't be ashamed to stop me. Okay, we will just discuss next time about donor exclusion and reverse osmosis. Thank you.